Hi, my name is Saipra Savang, and in this video, I'm going to present you our work called Learning Data Augmentation with Online Bilevel Optimization for Image Classification. The research task we are interested in is image classification. For this task, best results are obtained using convolutional neural networks trained with a large amount of annotated data. The problem is that it's not always possible to have access to large training datasets because of cost or technical constraints. Data augmentation is one way to mitigate this. In the context of image classification, it consists in creating new images from existing ones by applying class-preserving transformations. However, it has two main issues. First, data augmentation is dataset dependent. In the previous slide, you could see that after applying rotations or horizontal flips to a cat, it still remains a cat. However, in this slide, you can see that it can be a problem if you apply the same transformations to numbers. Second, data augmentation requires prior knowledge. If defining useful transformations for natural images is quite straightforward, it requires expert knowledge for specific domains like medical imaging. To address those two problems, we propose an approach where we train an image classifier jointly with an augmented network that will learn to perform data augmentation automatically by generating a distribution of transformations, minimizing the loss on a validation set. We formulate the problem as a bilevel optimization problem, where we train alternatively the classifier network in the outer loop and the augmented network in the inner loop, with the objective to find the best data augmentation parameters theta that will minimize the classification loss on the validation set. Solving the bilevel optimization problem exactly is very expensive, because it requires for each set of parameters theta to train the classifier network's still convergence. So, to make the training computationally feasible, we propose to use the gradient of the validation loss to update directly the augmented network. Nonetheless, even with this, the training is still slow, and so to make it even more faster, we use two approximations. First, instead of computing the exact value of omega star, we estimate it at each training iteration by taking only one step of gradient descent to update omega. And second, instead of computing the real gradient of the validation loss, we only enroll one iteration of the gradient of the training loss to get an estimation of the validation loss, and we use the gradient of this estimation to update the augmented network. By doing this, we get training time comparable to a standard training and good empirical results. We observed that training a classifier with our approach yields better results than training a classifier with predefined data augmentation, and this on 5 different data sets. Compared to other methods, our approach obtained better results than GAN-based data augmentation approach, and is very close to search-based data augmentation approach that gets better results because they use additional transformations to train their models, like non-differentiable transformations. I invite you to take a look at our paper to see more interesting results. To conclude, we propose a non-line differentiable approach for learning the optimal data augmentation using a validation set, which efficiently optimizes a large transformation network that learns to perform data augmentation automatically and achieve comparable or better results than conventional methods on 5 different datasets. Our code is available on GitHub. Thank you for your attention.